Hello, and welcome to class number 26 of Physics 218. So, last time we introduced the time-independent Schrödinger equation, and we learned how the solutions of this equation are known as stationary states, and that they have a well-defined time dependence. We then started to look at solutions of the time-independent Schrödinger equation for the infinite square well potential energy, which looks like this, right? The potential energy is 0 between 0 and L, but is infinity everywhere else. So we worked out what the allowed energies, that is the energies that solve the time-independent Schrödinger equation. We worked out the allowed energies as well as what the stationary state wave functions look like. This, remember, is our ground state with n equals 1. Here's our first excited state with n equals 2. What I'd like to do today is the following. I'd like to talk a little bit more about what this all means. In particular, what is a particle that's in one of these infinite square well stationary states actually doing? Second, I would like to begin taking our first steps towards understanding time evolution in general. Namely, if I have some arbitrary initial wave function, so if I know the wave function, the full wave function as a function of x at time t equals 0, what is the wave function at all subsequent times? So this is a deep and rich story that's going to take us a couple of classes to unfold, but we'll start to take a stab at it in the rest of today. So to start us off today, I'd like to have us all think about a clicker question about a particle in the n equals 2 stationary state of the infinite square well. So there are a couple of ways you could think about the question of what is the uncertainty in momentum for this wave function. So I'll talk about these two different ways that I can think about it. So one approach is to think about using the Heisenberg uncertainty principle. And I'll just abbreviate Heisenberg uncertainty principle as HUP so that I don't have to write out the entire thing. Right? And you know from the last chapter that the Heisenberg uncertainty principle says that delta x, delta px has got to be larger than h bar, or equal to h bar over 2. Okay, so let's think about this wave function, right? So we know that for this wave function, it's non-zero between 0 and L, but then it's 0 outside our well. We don't necessarily know the answer exactly for what delta x is without doing a long calculation. But making an order of magnitude estimate, right, the uncertainty in position here has got to be at least roughly on the same order of magnitude as the width of the well, which is L. So now, this is really important, right, because if delta x is finite, right, well, then this can't be 0. So that, it can't be 0 because that would violate the Heisenberg uncertainty principle. You might also think, well, how do we know that the momentum uncertainty isn't infinite? Well, we'd have to do a more rigorous calculation to see that, but one could imagine that, right, this is also not a state where and this is not a wave function where the position uncertainty is 0. The wave function definitely, or the probability density definitely is non-zero over a finite region, right? And so here we're a little bit more hand wavy, but our probability density looks something like this, right? So this is non-zero, so at least maybe it's suggestive that the momentum uncertainty probably isn't 0. It probably isn't infinite either. And the more formal way to see this is sort of qualitatively. Right. We know that this wave function is pure real. So we know that right, we know from our theorem about uncertainties that the uncertainty of momentum squared looks like this, but we know that since the wave function is pure real, the expectation value of px vanishes, right? And so we're left with this, right, which we know goes like, right, this goes like, so I'll just write this as proportional to, let's sort of put it the other way. It goes like h bar integral of psi of x star, which is just psi because it's real here, d squared psi, or d squared psi dx squared dx, right? We have another situation here where in the left half of the well, our wave function is concave down. Here it's concave up, right? The concavity, or the second derivative, always has the opposite sign as the wave function itself. And so this integral is definitely going to come out to be non-zero, but it's not going to blow up either. So what we find is, in fact, the momentum uncertainty here is non-zero but finite. And in recitation on Thursday, we will, I think, go through a bunch of detailed calculations analyzing these infinite square well stationary states. The next question I want to address is the following. So if we had a particle in some stationary state of the infinite square well, maybe the n equals 2 state for sake of argument, what is the particle doing, and is it moving? So let's just write down some things we know about what this particle is and isn't doing. So we just showed, right, we just argued that the uncertainty in momentum is, I'll write that is greater than 0. So there's certainly some spread in possible values I could measure if I were to go and measure the particle's momentum. So maybe that tells us something. We can also see that, right, for this state, right, the system of the energy of the system is also greater than 0. And because this is an infinite square well, all of the system energy is in fact kinetic energy. Right? This is, and the reason all of the system's energy is kinetic is that, right, within the well, we know that the particle is not interacting. The potential energy is 0. But because the wave function vanishes outside the well, right, there's no probability for the particle to be anywhere other than where the potential energy is zero. So in fact, the entire system's energy is kinetic energy. And well, if you have kinetic energy greater than zero, well, maybe that suggests that something's going on, right? Let's continue to think about this though, right? Because on the other hand, yeah, I'll switch to. Let's see if that's not showing well. I'm going to have to go out and buy another pack of dry erase markers. I'm running out of the ones I grabbed out of my office in haste, what feels like an age ago. We also know, right, on the other hand, our probability density, right, so let me just write, this is a full wave function, right, that probability density is constant. Right? It's constant because this wave function, this is a stationary state. And we know how that time evolves, as we saw last time, right? So if we, so the time-dependent wave function is associated with this, I'll write it as big psi sub 2, right? That we know goes like psi 2 x times this e to the minus I e 2t over h bar, right? And as we talked about last time, when I take the modulus square of this, right, this oscillating exponential factor multiplies to 1. So we get a constant probability density. So that's maybe sort of hard to reconcile with everything we said over here. So what's going on with that? There's something that's even weirder, right? So notice if you look at the probability density, notice that the probability density vanishes halfway across the well at x equals L over 2. So we'll use black here, 0 probability for being at x equals L. Okay. So this particle is ostensibly moving somehow, but yet it can't be in the middle of the well. And the probability density doesn't change in time, but we can see here that the wave function does change, right? You can see from this expression that when t equals 0, or more specifically, when e2 times t over h bar equals 0, or pi, or 2 pi, or 3 pi, etc., right, this wave function is going to be, the full wave function will be pure real, because that complex exponential is going to be 1 or minus 1. Conversely, right, if e2 times t over h bar is a multiple of pi over 2, so like if it's pi over 2 or 3 pi over 2, 5 pi over 2, etc., this factor is going to be I or minus I, and we get the wave function, the full wave function being pure imaginary. Right, so the wave function does change. So it varies with time. And we'll look at that and at how in more detail through a simulation later today. So what's going on here? The best we can say is that, right, the question, is it moving, turns out to not really be the right question to ask. What does it mean, really, for something to be moving? All we can really say is we can say what the particle is doing in terms of concrete things we can measure or calculate, so we can say something definitive about the momentum uncertainty, for instance. if in physics 421, I think you would learn how to calculate the probability of measuring a particular value for the momentum of a particle in this state. If anybody's really curious, I might be persuaded to make a bonus video about it. Involves a little bit of math beyond what we've probably seen, but it's really cool. And then all of this, right? So what we can say for sure is sort of what the particle isn't doing. So the particle is not sloshing or bouncing back and forth. Right? The problem with thinking in those terms is that, remember, this is quantum mechanics, right? This is a case where the particle does not have a definite position. Right? If our particle doesn't have a definite position, then it's really not meaningful to say, well, is this particle moving or not? All we can say are the things that we know how to rigorously think about, so we can say something about its momentum or its energy. One more remark I want to make. It turns out that the reason that the expectation value p sub x is 0 for this wave function, it turns out there's equal probability for it to be going in the plus x direction, or specifically to have a momentum in the plus x direction, as the particle is to have a momentum in the minus x direction. And so when you average all that together, that's why the expectation value of p sub x vanishes. So, as an aside, there's one more thing that I want to mention, and this was not discussed in the Townsend reading, and that is the idea that measurement invariably changes the wave function. In my opinion, this is probably the weirdest property of quantum mechanics. I think it's fairly safe to say nobody really deeply understands this. I'll say more about why we think this is the case, but if you think this is really weird, you should, because it is really weird. Okay, so what do I mean by this? So suppose that at time t equals 0, I have a wave function, and for a particle in an infinite square well. And let's just suppose that at this time, it's in the n equals 2 stationary state, right? We already know that, as long as we don't do anything to the system, right, we know how to calculate how the wave function subsequently evolves. In time, we just tack on that e to the minus I e2t over h bar factor. The question is, what if at time t, some later time, I go and I measure the position of my particle? So suppose I measure position at some time t, and that I find at some value that I'm just going to call x0. It turns out that this does something to the wave function, and it's called the collapse of the wave function. What happens is the following. The wave function, right, so the wave function ends up collapsing or changing into some really narrow spike. So you can think of this as a function that's really narrow yet really tall. So I'm gonna basically draw it like this, right? The wave function turns into this, something like this, where it's sort of 100% at x equals x naught. So, and this is called collapse of the okay. This is weird, right? There's nothing in our classical experience that gives us a context for measurements perturbing or sort of completely changing the state of the thing that we're measuring. You can try to make some hand-wavy arguments about, right? If you have a particle and you shine light on it, right? The light that you shine on it is gonna scatter or reflect off the particle and therefore sort of perturb it, maybe change its momentum by a little bit. But and that's all well and good, but that still doesn't really explain this, that the wave function changes in a quite specific way if you make a position measurement. There's also a sense in which the wave function changes if you were to try to make a measurement of the system's of the particle's momentum, and then we'll talk more next week about what happens if you make an energy measurement as well. But so the question is that we might ask about this is, well, what does the wave function do next? We don't have the tools right now to answer the question, well, if I measured my position, I collapsed my wave function to the spike, I don't know yet how to predict what's going to happen to psi subsequently, but we're going to be able to answer that question over the next 2 or 3 classes. So as a first step towards understanding the general time evolution of quantum states, what I'd like us to consider is the following. Suppose I have a particle in an infinite square well that is described by the following wave function. It's what we call a linear combination of 2 stationary states. So I have a constant times the psi sub 1, the n equals 1 stationary state, the ground state, plus a constant times psi sub 2, the n equals 2 stationary state. Now, it turns out that this psi still solves the time-independent Schrödinger equation. The time-independent Schrödinger equation turns out is a linear differential equation, so you can form linear combinations of solutions and still solve the equation. And if you're worried about this, you can go and plug this in and convince yourself. It also turns out, for reasons we will discuss at greater length on Wednesday, that this is still a correctly normalized wave function. You can go and check it if you really wanted to. So, well, how does this evolve in time? This okay, so if this is the wave function at, say, t equals 0, I'll write that down. So it goes at t equals 0. Right. Well, we know the answer. We know that the full time dependent wave function is going to have to look like 1 over root 2 psi 1 of x. We just have to tack on the appropriate exponential, complex exponential time factor, minus e to the minus I e 1t over h bar, and then the same thing over here. again, we have just different exponential, complex exponential oscillating factors on each term. So then the question is what does this do? And what happens to the probability density? So Townsend goes through an analysis of this, just using this straight math, and that's all well and good. But I think it's going to be more helpful for us to try to visualize this with a simulation. So we're going to study what happens with the time evolution of a wave function like this using a FET that we'll actually revisit a bunch of times in the next few weeks. So what I'll do in a second is I'll cut to my laptop, I'll show you the FET, and then I've put together a little packet of things for you to try and think about as you explore that simulation. Okay, so here are some things in the quantum bound states FET simulation that I wanted to show you. For sort of computational reasons, this simulation doesn't deal with infinite square wells. It does a finite square well, but we can sort of tweak things so that it's approximately infinite, namely if we make this well as high as we can go, right, if I drag this all the way up, we'll get this close to the infinite square well. So I can also change the width of the well by dragging this slider here. You also have the option of changing the well parameters by clicking this configure potential button. So we'll keep the height for now at 20 electron volts and the width at 1 nanometer. So right now what they've plotted here is the ground state probability density. And that's, I get that if I click E1 here. If I mouse over to E2, that will give me something that corresponds to the probability density for the n equals 2 state. And you can see it's not quite the same as the true infinite square well state, right? You can see this is sort of, there's a little bit of tapering as this dies off right at the edge of the well here, but it's a good approximation like our infinite square well stationary states. Now right now we're plotting the probability density, but we can also plot the wave function. And this is probably where it's easiest to see the correspondence we talked about. So here this now looks like our n equals 1 wave stationary state, n equals 2, n equals 3 here if I click there. And I can also change this to plot, right now I'm plotting the real part. I can also plot the imaginary part, which we assume is 0 at t equals 0, as well as the magnitude of my wave function. So I'm going to do the phase is more confusing than helpful, I think, so we'll just do that. And let me select this to psi 1 here. And so the cool thing about this is that if you click play, you can now watch the time evolution. So here we see the imaginary part of the wave function changing, as well as the real part changing. And then notice, however, that the magnitude, right, the real part squared plus the modulus squared of the entire thing, right, the magnitude doesn't change. And if we switch back to probability density view, we can see that that doesn't change either, in accordance with what we know about this being a stationary state. So I'll pause that. So you can pause, you can rewind, you can manually advance, you can change the speed at which time is moving forward with the slider here. Now the cool thing, the really cool part of this, is that you can put the particle into a superposition state. So we can dial up the one we looked at, we were looking at in Townsend, in particular, so I can put in, if I want to have an equal mixture of psi 1 and psi 2, I can put in 1 here for this box C1. I can put in a 1 there too. Now I do have to normalize so that so if I click that, that automatically adjusts those two constants. So this is in fact 1 over the square root of 2. And then I think I just have to click apply. Yep. And then close. So again, so you can see what the probability density looks like, and as well as the wave function. And this time, some interesting things happen, right? So as you saw in the reading, right now, as time goes on, our probability density sloshes back and forth within the well. So in the packet for the rest of today, you can explore this behavior for yourself. I want you to watch what happens and think about it physically, and then we'll continue this discussion when we come back on Wednesday.